In this recording, we're going to be defining something called zero divisors. But before writing down the definition, I want to motivate it by looking at some examples. And we're going to start by looking at reviewing some things that we know about the ring of integers. Inside the ring of integers, there are two basic facts that you've known for a long time. If we happen to know that a is not equal to 0, and we also know that AB is equal to AC, then it's no surprise we can conclude that B is equal to C. This particular fact is often called a cancellation law. So this is called a cancellation law. The one that I've written in particular would be a left cancellation law. There is a similar right cancellation law inside the integers. The right cancellation law for the ring of integers would say that if a is not equal to 0 and b times a is equal to c times a, then we know that b and c are exactly the same thing. And I'm going to call this fact 1. Now we've got another fact about integer arithmetic that is also important, and I want to write it down as well. And inside of the ring of integers, we also know that if a product is equal to 0, then either a is equal to 0 or b is equal to 0. And it's important to realize that neither of these facts applies in arbitrary rings. So neither of these facts is true in all rings. And what we're going to do in the rest of this video is we're going to investigate some examples where one of these facts falls apart. So let's start looking at an example. So we're going to look at the integers mod 12 under modulo 12 arithmetic. So in Z12, what I want to do is I want to look at the multiples of 3 modulo 12. So all of my calculations are going to be reduced mod 12. Well, 3 times 0 is equal to 0, 3 times 1 is equal to 3, 3 times 2 is equal to 6, and 3 times 3 is equal to 9. Now when I look at 3 times 4, that's equal to 12, which reduces down to 0 mod 12. And 3 times 5 is equal to 15, which reduces to 3 mod 12. And 3 times 6 is equal to 18, which reduces to 6 mod 12. And 3 times 7 is 21, but that reduces to 9 mod 12. And when we look at 3 times 8, that's 24, but when we reduce it mod 12, we get a 0. 3 times 9 is equal to 27, but that reduces to 3 mod 12. And 3 times 10 is 30, but that's equal to 6 mod 12. And 3 times 11 is equal to 33, which is equal to 9 mod 12. And one thing that I want to notice immediately from this is that in Z12, 3 is not a unit because there is no multiplicative inverse for 3 inside Z12. And I know that because 3 times x was never equal to 1 mod 12. No matter what value for x I plug in, So no matter what value I put in for x, I'm never going to get 1 when I do the multiplication. But there's another strange, odd thing going on in Z12's multiplication as well, and that's these two facts here. 3 times 4 is equal to 0, and neither 3 nor 4 is equal to 0. And 3 times 8 is equal to 0, and neither 3 nor 8 is equal to 0. But we have other weird facts as well. 3 times 5, and 3 times 9, and 3 times 1 are all equal to 3. And so we can't cancel either. And so I want to write those two things down explicitly. So in Z12, 3 times 4 is equal to 0, but 3 is not 0, and 4 is clearly not 0. And it also in Z12, we have 3 times 5 is equal to 3 times 9, but clearly 5 and 9 are not the same thing when we're doing arithmetic in Z12. So what this means is that we have two basic ideas. In Z12, we have what are called zero divisors. Namely, 3 times 4 is equal to 0, and 3 is not 0, and 4 is not 0. And in Z12, we cannot cancel. And what I mean by cancel, well, first of all, get that written properly. We cannot cancel. And what I mean by this is, if I know that A times B is equal to A times C in Z12, we can't say B is equal to C. And the reason we can't do that is this right here. If A is equal to 3 and B is equal to 5 and C is equal to 9, 3 times 5 is equal to 3 times 9, but 5 and 9 are not the same thing. So what I want to do now is I kind of want to formally define what a zero divisor is, and then we'll look at one more example. So let's let R be a ring. If A and B are non-zero elements, and we happen to have A times B is equal to 0, then we call A and B a pair of zero divisors. If R is commutative, this next bit doesn't make is not particularly important. But if R is not commutative, and we have A times B is equal to 0, we're going to call A left zero divisor, and we're going to call B a right zero divisor, because it turns out that the multiplication is not necessarily commutative. In other words, if R is not commutative, then it's possible for A times B to equal 0, and B times A may or may not equal 0. And I want to actually look at that particular idea and make it very concrete. So we're going to actually look at a specific example inside of the ring of 2 by 2 matrices. I'm going to let A be the matrix 3 minus 2 0 0, and I want to let B be the matrix 4 negative 2 6 minus 3. And what I'd like you to do is I'd like you to stop the video and I'd like you to find A times B. Hopefully you did that, and it's not very hard to find A times B. A times B looks like this. So we write the two matrices down, and the answer, of course, is going to be a 4 by 4 matrix. The entry up here is going to be this row dotted with this column, and when we do that product, we are going to have 12 minus 12. The entry here is going to be this particular row dotted with this particular column, and that's going to wind up being 6. It's going to be minus 6 plus 6. And the entry down here is going to be this 0 row dotted with that, so it's just going to be a big fat 0. And this entry here is going to be that 0 row dotted with a second column, and so that's also going to be a big fat 0. Now when we simplify the arithmetic, we wind up seeing that we've got a pair of zero divisors, because neither of these matrices is equal to the zero matrix. In other words, we can say that A and B are zero divisors. Since A is not the zero matrix, B is not the zero matrix, but AB is the zero matrix. Now, the thing right now that I want to notice is that A is on the left side of this product, so A is a left zero divisor, and B is a right zero divisor. It is worth looking at what happens to B times A. So B times A would be 4 negative 2 6 minus 3 times A, which is 3 negative 2 0 0. Again, you should stop the video and compute this for yourself. And hopefully you did that. And when we do compute it, what we're going to wind up with is, let's see, we have this particular row dotted with that, so we're going to wind up with a 12 in this first spot. Now we're going to have this dotted with that, and that's going to be a minus 8. And down here, we're going to have this row dotted with that column, and that'll be an 18. And the final entry in our product is going to be this row dotted with that, and that's going to be a minus 12. And that matrix is certainly not the zero matrix. So with this pair of zero divisors, we have to have A on the left and we have to have B on the right. In other words, to just sum everything up, in this case, A times B is equal to the zero matrix, but B times A is not the zero matrix. So it's important to realize that while we have this particular fact being true, we also have that AB is not equal to BA. And that means that in a non-commutative ring, which way you multiply two zero divisors together does matter. And that's it for this video.